In this video, I'm going to go over your Unit 6 review for AP Calculus. This is all about applications of the definite interval. So our first problem is a particle motion problem. A particle moves along a straight line. For 0 is less than t is less than 6. The velocity of the particle is given by this equation here. The position of the particle is given by s of t, and it is known that s of 0 is 3. So before I even start my problem, I'm going to go ahead and enter my equation into my calculator. Once I have it stored in my y1, I can do whatever I want with it. I can do integrals, derivatives, function values, graph it, all that good stuff. So our first question says, find all values of t in the interval from 2 to 6 for which the speed of the particle is 1. Well, the speed of a particle is going to be the absolute value of velocity. So what I'm going to do, I'm not going to graph this, but what I'm going to graph is the absolute value of y1. And then I'm also going to graph 1, because I want to know when that absolute value of the velocity is equal to 1. For my window, my x values are going to go from 2 to 6. And then for my y's, I need to be able to see 1. So I'm going to go from, let's say, 0 to 2. And then we'll graph. Okay, so there are two values where my speed is going to equal 1, and it's going to be at these two locations. I'm going to calculate the intersection. First curve, second curve, and then we'll guess. Okay, so our first value is, we want this to equal 1, is 2.957. My second value, if I do that, is 5.7296. So we always want 3 decimals, more is better. So those are those two locations. Okay, find the position of the particle at t equals 4. So for that, we're going to use our fundamental theorem that says if I integrate from 0 to 4 of my velocity equation, that's going to give me the antiderivative, which is my position, which is going to be s at 4 minus s at 0. So I picked 0 because I know the position at 0, 4 obviously, because that's what I want. This I'm going to get in the calculator. S of 4 is what I'm solving for, and S of 0 is 3. Okay, so here we're going to integrate from 0 to 4 of my y1, because that's where my velocity is stored. That gives me negative 9.98756, and then I'm just going to add 3 to that. So my position at 4 is 2.0124. Next, it says find all times in the interval at which the particle changes direction. Okay, so I'm going to go to my y equals. I'm going to get rid of those two. I want to highlight that one. Now what I'm looking for is where my velocity changes sign. So when my graph goes from either being positive to negative or negative to positive. So my window, we're going to adjust, is going to go from 0 to 6. And now I want to see negative values. So before I was just looking at 1. Now let's go from like negative 2 to 2. And we're looking for where it crosses the x-axis, which in this case is just that one location. Okay, so now we're going to use that calculate menu again, and I want to calculate the 0. I want to go to the left of it, to the right of it, and enter, and we get 1.8063. Justify our answer. V of t changes signs. Find the total distance traveled. total distance traveled, we're going to use the integral from 0 to 6 of the absolute value of v of t. If we just integrated v of t, we'd find the displacement, but we want the absolute value, which is going to account for the fact that we were traveling to the right and then we were traveling to the left, so we want that distance and that distance. If we just integrated, we would have our displacement. So we're going to use our integral. We're going to do the absolute value of y1. And it's going to take a little bit, but our answer is 6.3935. Okay, last one with this equation. Find the average velocity of the particle from time period 0 to 6. So this is the average value of the function, which is going to be 1 over 6 minus 0 times the integral from 0 to 6 of our function. Type all that in the calculator, and we're going to get a negative 0.7066. Next problem, we have a table here. It says the temperature of the water in a tub at time t is modeled by a strictly decreasing twice differentiable function. W, where Wt is measured in degrees Fahrenheit, and T is measured in minutes. At time 0, the temperature of the water is 55 degrees. We got that in the chart. The water is heated for 30 minutes, beginning at t equals 0. Values of W of t are in the chart above for the first 20 minutes. Use the data in the table to approximate the rate at which the temperature of the t is changing at t equals 12. Okay, 12 is right in the middle here, so we're going to be looking at W of 15 minus W of 9 over 15 minus 9. From my table, that's 67.9 minus 61.8 over 15 minus 9. Now you do have a calculator. You can leave it just like this. If we do it in the calculator, we get 1.0166. Okay, next, it says, using correct units, explain the meaning of 1 over 20 times the integral from 0 to 20 of W of t. And then we're going to use a left Riemann sum to estimate that. Okay. So the integral from, 1 over 20 times the integral from 0 to 20 of W of t is going to give us the average temperature. It's going to be the average value of the function, and since this function is giving us temperatures, it's the average value, or average temperature of the water from t equals 0 to t equals 20. Now we're going to do a left Riemann sum to approximate this. So we're going to have our 1 over 20, and then I'm going to have my left Riemann sum. So remember, we're doing rectangles here. We're going to get the widths from the difference between our t values, and then our heights are going to be evaluated at the left side. So my first one is going to be 4 minus 0 times 55.0. My next one is going to be 9 minus 4, and then we're evaluating at 57.1. Okay, next one from my table is 15 minus 9, and we're evaluating 61.8. And then we have 20 minus 15, and the left side there is 67.9. Okay, again, you can leave it just like this. If you do type it in the calculator, you're going to get 60.79. Last one. Evaluate the integral from 0 to 20 of W prime of t. Using correct units, explain the meaning in the context of the problem. Well, all I have to work with is that table. So somehow I have to get this from the table. But just like we did on the previous side, we're going to use the fundamental theorem of calculus that says this integral is going to be the antiderivative of W prime, which is going to be W evaluated at 20 minus W evaluated at 0. So from my table, I'm going to get 71 for W, or W of 20, and 55 for 0. Okay, this gets me 16. So what does this mean? Well, this was the temperature at 20. This is the temperature at 0. That means the temperature went up 16 degrees. Okay. So like I said, the temperature went up 16 degrees from T equals 0 to T equals 20. Okay. Our next problem. On a certain day, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by this function here, where T is measured in hours and we're between 0 and 8 hours. At the beginning of the workday, there is 500 tons of unprocessed gravel. During the hours of operation, 0 to 8, the rate in tons per hour at which the plant processes the gravel is modeled by P of T equals 100. So first it says find the total amount of unprocessed gravel that arrives at the plant during the time interval 0 to 8. That's our classic using our integral. We are integrating from 0 to 8 of G of T dt. So I've already typed this in my calculator. If we integrate, we get 825.551 tons. Okay. Next, we want to, is the amount of unprocessed gravel at the plant increasing or decreasing at T equals 5 hours? So what I want to find is what the rate is coming in and what the rate is going out. Well, we already know rate going out is just a constant 100. No matter what I type into that equation, I'm going to get 100. So we want to figure out what G of 5 is. Okay, so I have my equation in y1, and we're just going to evaluate y1 at 5. We get 98.140. Well, if the gravel is coming in at a rate of 98 tons per hour, and they are processing that at 100 tons per hour, that means the amount's going to be decreasing because you're processing it faster than it's coming in. So a little bit more formally, the amount of unprocessed gravel is decreasing because G of 5 is less than P of 5. Our final question, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? Justify your answer. So anytime you are asked for an absolute max or an absolute min on a closed interval, we are using the extreme value theorem that says that an absolute max and an absolute min on a closed interval, as long as our function is continuous, will occur at an endpoint or a critical point. So I'm going to make a chart. And I'm going to make up a function A of T, amount. Okay. So my equation is going to be A of T. We have three things to consider. We have the amount that we started with, which was 500. Then we're going to add the amount that goes in. And then we're going to subtract the amount that goes out. Make these X's. Okay, so that's my equation we're going to use. My endpoints are going to be 0 and 8, and then I want to calculate my critical points, or find the critical points. So if I take the derivative of this, this is going to be 500 plus G of T derivative of 500 is 0. Minus P of T. So if I set that equal to 0, and I'm going to go ahead and replace that with what P of T is, which is just 100. What I'm looking for where is G of T equals 100. So to do that in the calculator, I've got my equation. I'm going to type in 100 and then our window. We want to go from 0 to 8 because that's our window. And then I need to be able to see 100. So I'm going to go from like 0 to 200. As long as you can see 100, then we're good to go. So then we'll graph and find the intersection. Okay, so I'm going to calculate the intersection. I'm just going to do enter, enter, enter. So that value is 4.9234. Now, before I lose this, it's currently being stored in my X. So I'm going to go here and I'm just going to do X store in A, whatever letter you want. So now I have that stored. So when I do the calculation with it, I don't have to worry about copying down a whole lot of numbers or transposing or anything like that. Right. So the amount at 0, I don't have to do a calculation. That's just going to be 500. My amount at 8 is going to be that 500 plus the integral from 0 to 8 of my g function minus the integral from 0 to 8 of 100, which is just going to be 800, but we'll let that work. So we do that in the calculator, space here, I get 525.551. Okay, so we're trying to find the max. So right now, t equals 8 is our winner. But for our third one, I want to do 500 plus the integral from 0 to a, because I want that there, of y1 minus the integral from 0 to a of 100. And it is 635. Okay, so it says, what is the maximum amount? This is our maximum amount. This is our justification, but we're going to go ahead and state our answer. Okay, for my answer, I'm going to cover all my bases. It asked what is the maximum amount. So what we're looking for is that 635. But the maximum amount of unprocessed gravel is 635.376 tons and occurs at this value. Because sometimes they might ask you for when, sometimes they might ask you for how much. So by answering both, you are covered. Okay. Now we're going to find the area of the region bounded by 6x minus x squared and y equals x squared. We're going to show a graph, a definite integral, and then we're just going to use our calculator to get the value to make our lives easier. So let's go ahead and graph this. Okay. I'm just going to go on a standard window, which will go to a negative 10 to 10. Okay, so the region bounded is going to be this right here. If I calculate that intersection, which you could do by hand, but since we have the calculator, we'll just use that. If you needed to find this, what you would do is set the two equations equal to each other and solve. You'll get two solutions since there are two, but we already know that one's 0, and our second one is at the point 0.39. So I'm going to go ahead and graph this. Okay, so here's my graph. And what we want is the area bounded by here. So it's always going to be top minus bottom. So this is going to be the integral. We're going this direction, so from 0 to 3 of our top, which is 6x minus x squared, minus the bottom, which is x squared. If I were going to do this by hand, which we absolutely could, I would simplify, combine your like terms and all of that. But for this test, you can just type it in your calculator and move on, because I'm just concerned about can you get the setup of it correct. Next, let R be the region bound by the graph of x equals the natural log of y plus 2 the vertical line x equals 6, and the horizontal lines y equals 1 and y equals 5. So we have horizontal lines at 1 and 5. And we have a vertical line at x equals 6. And then we have this, which you could graph in Desmos, but we won't have that for the test. So if I solve that, x minus 2 equals natural log of y, that means y is going to be e to the x minus 2. So if I graph that, it looks something like that. So 6 is somewhere over here. It's going to cross, if I'll go ahead and draw my y equals 5 line. Okay, x equals 6 is going to be out here, so we're graphing this. I'm going to cross it too and go like that. So we're trying to find this area here. Okay, the issue is if I did this with my cross sections being vertical, I'd have to do 2 different integrals, which is fine, and we can do that. But what I'm interested in is, can we do it with our cross sections going this direction? Because there, this one's always to the right and this one's always to the left. So I can do it that way. So if we're going this way, we're integrating from 1 up to 5. And then the right is going to be 6. The left is going to be our natural log of y plus 2. Okay, then I type that in my calculator. Oh, right. Just write the integral. I don't need to type it in the integral. We're good. Okay, here, the shaded region for the figure is bound by the graphs of root 9 minus x squared, so that's this semicircle here, and the lines x equals -5, x equals 5, and y equals 4. What is this area? Well, essentially what I'm going to do here is I'm going to find the area of this rectangle, and I'm going to subtract the area of the semicircle. So the area of the rectangle would be, we're going from -5 to 5, so that's 10, and a height of 4. And then I'm going to subtract. You could do this one by hand, but the one on the test is not one you can do by hand. So we're going to integrate from -3 to 3 of that. Okay, again, you could do that just half of a circle. But if I do that, we get 25.863. Okay, next we have R is the shaded region bound by the graphs of the square root of x and e to the -3x. And vertical line, x equals 1. So we're going to find the area of R. So first I'm going to graph it. Okay, so there's my square root. And there's my e, and we're also bounding it with a vertical line at x equals 1. So we're looking at this area here. Okay, so there's my sketch that I transferred from my graph. So now we want to find this area, which is going to be just the integral of top minus bottom. But to do that, I need to find this intersection point here. So I'm going to calculate the intersection. I'm going to call that P. This occurs at 0.2387, and I'm going to assign that P for point. Just like I did before, I'm going to automatically come out here. If For whatever reason, I chose P, so I'm going to do X, and I'm going to store it in P. You could use A again, like I did in the first one. Okay, but now it's stored, so anytime I want to use that intersection point, I can use the letter P. So I want to integrate from P to 1, because we're going from here to here, and it's top minus bottom. So that's going to be the square root of X minus e to the negative 3x. So like I did before, I can do the integral, and I can start at 0, and I can literally just type in P there because I stored that value. And actually, I've got these in my y1 and y2. Which gives me 0.4426. Now we want the solid if I rotated this whole thing around the x-axis. So we're rotating it around here, and we're getting sort of a one cape kind of thing. So my cross sections are going to look like this. So if I were to rotate that little segment around the y-axis, we get what's called a washer. So we're going to find the volume, find each of the washers, and add them up using the integral. So we're going to still be integrating from P to 0, or P to 1. And it's going to be pi r squared minus pi r squared. My cross sections are going to look like little washers, and I want the outside circle minus the inside circle to get that volume. My outside circle is going to be the square root. So I'm going to have the square root of x squared, so pi r squared, minus pi r. My inside circle is going to be e to the negative 3x. And we'll square that. The pi we can pull out because of the constant, but when we do this, you're going to get 1.358. Last, we're going to take it and rotate it around the line y equals 1. So y equals 1 is going to be right here. So it's the same cross section, but now I'm rotating it around this axis. So I'm still going to get my washer shape if I slice at any point here. But now my radii are a little bit different. So I'm still going to pull out my pi. We're still going to be integrating from P to 1. But now we need to think about the radius. The outside radius is going to be the distance from here to here. Well, the distance from here to here is going to be e to the negative 3x. The distance from here to here is 1. So what I want is 1 minus that area. So we get 1 minus e to the negative 3x. And then we'll square that for our outside circle. Then we're going to subtract our inside circle. Okay, my inside radius is going to be that distance there. Okay, the distance from here to here is the square root of x. I want the distance from here to here, which is going to be 1 minus that. Okay, and then we type it in the calculator. 1.424. Next, we have our known cross sections. So for our known cross sections, we are have a base, and we're going to be constructing cross sections of a specific shape. So for this one, the base is going to be between the graphs of x squared and the square root of x. So x squared is going to look like this. Square root of x is going to look like this. Okay, so this is our base, and our cross sections are going to be formed perpendicular to the x-axis. So the first, we're going to construct our squares. So we're going to be integrating from 0 to 1. And then the squares, if you can picture, this is the base of the square, and then we're kind of constructing a square here, is going to be this base times the height, which is going to be equal. Well, this is going to be the square root of x minus x squared. It's going to be top minus bottom, and then we're going to square that to get the actual square shape. Again, type in the calculator to get that. for semicircles. Okay, so now I'm taking this and I'm making a semicircle shape. So we're going to integrate from 0 to 1. We're going to have the area of a semicircle is 1/2 pi r squared. My r, if I look at my picture here, the distance from here to here is going to be the diameter. So what I want is just half of that. So I'm going to have my square root of x minus x squared, and then divide that by 2. So it's still the top minus the bottom to get that whole width, but I just want half of it. So 1/2 pi r squared. Calculator time. Last one, triangles with an altitude of 8. So triangles are 1/2 base times height. The base will be that top minus bottom, root x minus x squared. My altitude, my height, will be 8. Okay. Next one, let r and s be in the figure to the right be defined as the follows. R is the region in the first and second quadrants, bounded by the graphs of 3 cosine x and e to the x. That's R. And then S is the region in the first quadrant, bound by the 2 graphs, the x-axis and the y-axis. So now it says to find the area of S, which is just this first quadrant area. As I'm looking, we're going to integrate going across this way, but in each one, we're just going to integrate from here to whatever this point is of e to the x, and then from this point to this point of just the cosine function. So I need to find this point here, and I need to find this point here. So I'm going to calculate the intersection, which I've already done, and I'm going to label that as A. Don't assume it's 1. It's really close to 1. But according to the calculator, it's going to be 0.7685785. So what I did is I stored it in A. Okay, so I found that intersection and then automatically go out and do X, stow, A. Stored. Now I'm going to go ahead and find this point here. Let's go back to my graph and we're going to calculate the 0. Which gives me 1.5707 and a bunch of other stuff, but I'm going to go ahead, get out of here, X, store, B. Okay, so that guy's stored. So for my area, it's this area plus this area. So it's going to be the integral from 0 to A, because I've defined it over there, of, that one's e to the x. Then we're going to add that to the integral from A to B of 3 cosine of x. In a typical AP problem anymore, they would say like this is f of x and this is g of x, and then you could just use those rather than writing the equations. Okay, and again, when you type it in, you literally type in A and B because that's what we stored it in. Find the volume of the solid generated when R, this one, is rotated around the line x equals -2. So we're rotating this. We always want to draw a representative rectangle here so we can kind of track it and figure out our radii. So we're going to take this, it's going to rotate around. Again, we're going to get that washer shape. So it's going to be pi r squared minus pi r squared. So I'm going to pull the pi out. It's going to go from here to here. So I'm going to find this third point, which is a -1.4960, and I stored the rest of the values. I stored this one in C. So we're going to be integrating from C to A. And then it's going to be big R squared minus small r squared. So my big radius is from here to here. The distance from here to here is 3 cosine of x. We just need to add on this piece, which is a constant 2. So it's going to be 3 cosine x plus 2 squared for our big radius. Then we're going to subtract our little circle. So we've got pi r. The little radius is the distance from here to here, which is going to be this distance, which is e to the x, plus this distance, which is 2. So that is 72.417. And then last, region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with one leg across the base of the solid. Find the volume. So an isosceles right triangle is looking like this. So we're constructing those like here on this shape. The two equilateral sides are this side here. So it's just going to be the 3 cosine of x minus e to the x will give me that distance. So we're going to integrate from C to A, and it's 1/2 base times height, where both the base and the height are 3 cosine x minus e to the x. So I can just do that squared, or if it makes more sense to you to do this times itself, same deal. And we get 2.653. So this is your review for applications of integrals.